Welcome to The Explainer. We are absolutely surrounded by AI these days, right? But with all these claims flying around, how do we actually know which ones to trust? Today, we're going to give you the toolkit you need to look past the hype and actually verify what you're being told.
So let's just jump right in with a question where, the stakes are literally life and death. A medical AI is 99% accurate at detecting cancer. Sounds amazing, right? Almost perfect. The question is, should we trust it with our lives? Is that one number really enough? Well, as you probably figured, the answer is it's complicated. A single number like 99% accuracy isn't just a little bit misleading, it can be dangerously misleading. And today, we're going to break down exactly why so you can start asking the right questions.
All right, Section 1, the problem with averages. To kick things off, we've got to talk about something that sounds super basic, averages. But trust me, the way we find the so-called center of our data can completely change the story we think it's telling.
Okay, so the mean. We all know this one, right? The average, you add up all the numbers, divide by how many there are, boom. It's the metric we see everywhere. But, and this is a big but, it has a huge critical weakness.
And that weakness is its vulnerability to outliers, those extreme values. But we've got a way to fight back, and it's called the median. With the median, you don't really do much math. You just line up all your numbers in order and pick the one that's sitting right in the middle. It's a simple move, but it makes it way more resistant to getting skewed.
And this example just perfectly shows why this matters so much. So check out this company. The average salary is $136,000. Hey, that sounds great, right? But that number is completely thrown off by the one CEO making $1 million. Now look at the median salary, $50,000. It just ignores that one crazy high number and tells you what a typical employee is actually taking home. See? The median gives you a much more honest picture.
All right, Section 2, measuring the messiness. So, knowing the center is just part one of the story. Now we need a way to measure the spread, or, how messy and chaotic the data really is. And the go-to tool for this is standard deviation. Basically, it tells you how spread out your numbers are from the average. If you have a low standard deviation, it means all the data points are huddled up close to the average. It's super consistent. But a high standard deviation, that means your data is all over the place, way more unpredictable.
Now this is where it gets really interesting. Look at this. Both classes, A and B, have the exact same average score, 70. If you only looked at the average, you'd think they're identical. But look at the standard deviation. Class A has a tiny SD of 10. That tells us most students are scoring pretty close to 70. It's a really consistent class. But Class B? Whoa, a standard deviation of 25. That means scores are all over the map, from failing to acing it. Same average, completely different stories.
So, standard deviation gives us a great big picture view of the spread. But what about those individual points that are really far out? Those are our outliers. And we have to be careful because these things can absolutely wreck a model. They can fool an AI if we don't find them and deal with them first. The good news is we have a method for hunting them down. It's got a kind of nerdy name, the 1.5 times IQR rule, but the idea is actually super simple. All we do is find the range that contains the middle 50% of our data, the normal stuff. Then we build a statistical fence around that range. Any data point that lands outside that fence gets flagged as a possible outlier. It's like a security system for your data.
Okay, let's put this to work with a real-world example. Say we're watching the daily power consumption of a power plant. We do the math, we build our fence, and we find that a normal day is anything between 460 and 540 kilowatt hours. So, if one day we get a reading of, say, 459, bam, the alarm goes off. That's an outlier. Now, it could just be a sensor glitch, or it could be a sign that something is seriously wrong at the plant, and that's why we have to investigate.
All right, Section 3, the model's real report card. So, we've looked at how to check the data going into an AI, but now it's time for the main event. How do we grade the AI itself? How do we get its real report card? Something that goes way beyond that simple accuracy number.
And I'm going to repeat this because if you take away only one thing today, let it be this. Accuracy alone is not enough. Especially in a high-stakes situation like detecting cancer, we absolutely have to demand a more detailed breakdown of how that model is performing. And here it is. This is that report card. It's called a confusion matrix. And honestly, it's the best tool we have for really digging into an AI's performance. Because it doesn't just give you a single grade,
It shows you not just if the model was right or wrong, but how it was right, and, crucially, how it was wrong.
Let's start with the good stuff, the true positives and true negatives. These are our wins. A true positive is when the model correctly spots someone who has cancer. A true negative is when it correctly clears a healthy person. Simple enough, right? The model got it right.
Okay, now for the mistakes. A false positive. You can think of this as a false alarm. The AI flags a healthy person as having cancer. Now, this is definitely bad. It's going to cause a ton of stress and lead to unnecessary tests. But it's not the worst mistake the model can make.
Because this is the most dangerous error of them all, the false negative. This is a type 2 error, and it's a nightmare scenario. The AI says you're fine, predicts no cancer, but you're actually sick. This is a misdiagnosis. It means a sick patient gets sent home without treatment. In a medical context, this is the error that can be catastrophic.
And this quote just hits the nail on the head. Think about it. Let's go back to our original problem. If a disease is rare, say only 1% of people have it, a lazy AI could just predict no cancer for every single person. And guess what? It would be 99% accurate. Its accuracy score would look phenomenal. But it would be completely useless because it would miss every single person who actually has cancer. It's a perfect example of how a great accuracy score can hide a fatal flaw.
Okay, section 4, is the difference real? So the confusion matrix gives us the truth, but there's one last question we have to ask. Let's say we're comparing two AIs, and Model B has a slightly better score than Model A. How do we know that difference is, well, real? How do we know it's not just random luck or statistical noise?
For that, we turn to something called hypothesis testing. And the best way to think about this is like a trial in a courtroom. We put the new AI on the stand, and we start with the assumption that it's innocent, meaning it's no better than the old one. That's our null hypothesis. Then we present the evidence, our data. And only if the evidence is overwhelmingly strong, beyond a reasonable doubt, can we reject that initial assumption and say, yep, this new model is genuinely better.
And there are a bunch of different tests we can use as our legal tools. A t-test can compare the averages of two models. An ANOVA can compare 3 or more. A chi-square test can check for relationships, like if a model is biased towards a certain group. You don't have to be an expert on these, just know that they exist to give us that final confirmation that what we're seeing is real and not just a coincidence. Phew! Okay, section 5, trust through verification. We have covered a ton of ground here, from averages and medians to standard deviation and outliers, all the way to the confusion matrix. So let's wrap it all up.
So here it is, your verification checklist. You start with the basics. Look at the median, not just the average. Then you measure the spread with standard deviation and hunt for those outliers. And most importantly, you demand the model's full report card, that confusion matrix. And you pay very close attention to those critical errors, like false negatives. And finally, you confirm your findings with statistical tests. This is how we build real trust. It's not about blind faith in a single number. It's about a deep, evidence-based understanding.
So what does this all mean for you? It means the next time you see a flashy headline about some new AI, you're not just going to take it at face value. You'll know the questions to ask. You'll be thinking, okay, but what's the median? What's the standard deviation? And show me the confusion matrix. How many false negatives are we talking about here? The point isn't to turn you into a statistician. It's to empower you to be a smarter, more critical consumer of technology in this new age of AI.